Imagine for a moment you're standing in a laboratory. Maybe there's a reaction going on the bench in front of you, or maybe the whir of a centrifuge fills the air. Someone hands you a vial with maybe about a teaspoon-sized volume of an unassuming powder sitting inside. They tell you that within that single minuscule amount of material, there is a hidden internal surface area vast enough to cover not one, but two professional football fields, and still have surface area left over. This isn't a poetic metaphor. This is an actual measurable surface area, a landscape of molecular canyons and valleys, all contained inside a pile so small it could be scattered in a single puff of wind. This is the world of metal organic frameworks. To the naked eye, they look simple, perhaps no different from salt or sugar. But on the molecular level, they can be designed with such incredible precision that they can accomplish tasks that feel like they belong in science fiction. Welcome to the Chemist's Codex. My name is Peter, and I like to tell stories about whatever happens to catch my interest, because I believe those stories can teach us more about ourselves. Let's circle back to that mind-bending idea, a teaspoon amount of powder holding the same surface area as two football fields. It's a statement that seems to defy all common sense, a paradox that feels like it breaks the laws of physics, and yet, it's real. If you could somehow take just 1 gram of this substance and carefully unfold every single internal wall, each hidden surface within its structure, you would find yourself standing on a plane covering thousands of square meters. So how can we begin to wrap our heads around what a metal organic framework, or MOF for short, actually is? At its core, the concept is surprisingly elegant. Think of MOFs as the ultimate Lego set for chemists. In this set, you're building with metal atoms and rigid organic molecules. When you bring these two components together under the right conditions, something extraordinary happens. They snap into place, assembling into vast, intricate, and perfectly repeating crystalline cages. The secret to their spaciousness, and the reason they don't just collapse into a dense mess of ions and molecules, lies in the nature of the rigid organic linker molecules. They are specifically chosen to be long and rigid. This structural stiffness ensures that every pore they form in the material stays open, resisting the natural tendency to collapse in on itself. The result is a structure of incredible strength and cavernous emptiness. Now, imagine you are the architect of this molecular world. You get to choose your building blocks with absolute precision. For your metal hubs, you could select zinc, copper, iron, or zirconium, just to name a few examples, with each metal atom offering different geometries. Then you select your organic linkers. These are molecules of various lengths and distinct chemical personalities. Some might be long and thin, creating massive open chambers. Others might be shorter, creating tighter, more selective pores. This incredible modularity is the genius of MOFs. It allows a chemist to precisely tune the size and chemical properties of the pores within the molecular structure. This is precision on the nanometer scale, perfectly suited for trapping tiny hydrogen molecules or ensnaring comparatively massive viruses. Because this architectural blueprint is so customizable, chemists have already synthesized tens of thousands of distinct MOFs, each with a unique structure and properties. And while the mind-boggling surface area is the headline-grabbing feature, the true power of MOFs is this unparalleled customizability. It's the ability to dream up a function, say capturing a specific pollutant or storing a particular gas or delivering a certain drug, and then designing and building a material to execute that exact task. So then why brag about that microscopic acreage? Let's turn to something more familiar, your kitchen sponge. It's light, maybe a little springy, and mostly empty space. It's full of interconnected holes and pores, and its absorption capability is directly related to its surface area. The more holes in your sponge, the more surface area there is for water to cling to, and the more water it can soak up. Surface area, then, is sort of a measure of a MOF's potential. It's the potential to make contact with and capture a surprisingly large amount of a specific substance. And it's this surface area combined with the chemistry that selects for certain molecules that make MOFs worthy of the Nobel Prize. The story of metal organic frameworks begins in Australia, with a thoughtful and creative chemistry professor named Richard Robson. Like many chemistry professors, Robson used physical ball and stick models to teach his students about molecular geometry. Each year, as he brought out these teaching aids, watching students connect nodes and struts to build simple structures, a more ambitious idea began to form in his mind. Robson wondered if he could use the fundamental, predictable geometries of atoms as the basis for linking molecules into extended and highly ordered networks. Robson put this idea to the test in 1989. He chose his components carefully: copper ions, which naturally form his desired geometry, and a specific organic molecule that was able to form 4 distinct bonds with the copper ions. Most chemists at the time thought this was a recipe for a chaotic mess, predicting mixing the copper ions with the organic molecules would form a tangled, disordered rat's nest of uselessness. But that didn't happen. In a moment of profound discovery, Robson's bold prediction proved correct. The copper ions and the organic linkers didn't collapse. Instead, they organized into a vast, repeating, 3-dimensional pattern. And the geometry Robson selected for, the 4-armed linker and the copper ions, formed an analogous structure to diamond. But where a diamond is dense and compact, Robson's new crystal was the opposite. It was a lattice of incredible openness, defined by large, empty cavities. Energized by his success, Robson expanded on his findings, creating several other new constructions by varying the metal and linker components. He began to explore the properties of the voids in the architecture. In a particularly noteworthy experiment, Robson filled the cavities of one of his frameworks with one type of ion. He then submerged the entire crystal into a solution saturated with a different ion. Just as he hoped, the ions exchanged places, with the new ions moving into the framework while the original ions moved into the solution. This experiment showed that these frameworks weren't static, empty cages. They were systems in which substances could freely move in and out of the internal structure. There was a pretty significant catch, though. Robson's constructions weren't particularly stable. Because of this instability, many chemists dismissed them as interesting chemical curiosities, but ultimately useless for practical applications. But the seed had been planted. Robson's experiments had shown that if these frameworks could be designed with sufficient stability, they could be optimized to interact with specific molecules. And there were enough chemists who could see that Robson was onto something. The next major chapter in the story of MOFs takes us to Japan, and to the work of Susumu Kitagawa. Kitagawa's research was guided by a profound and patient philosophy, to seek out the usefulness in what is commonly considered useless. He was drawn to ideas that others dismissed. This mindset made him perfect for finding use in Robson's useless constructions. Kitagawa's first forays into these molecular constructions yielded what seemed, at first glance, to be another useless material. It was a 2-dimensional structure that could hold acetone molecules. Like Robson, Kitagawa used copper ions as the cornerstone of his structure. However, the structure was still fragile and didn't possess the robust porosity that would be needed for practical use. This lack of immediate utility created professional obstacles for Kitagawa. He struggled to get funding for his research, as funders were skeptical of any use that these structures could have. The frameworks being created were still too unstable and largely useless. I mean, why pour money into developing materials that fall apart when you try to use them? Even so, Kitagawa kept at it, convinced there was something here. And in 1997, Kitagawa's research group had a breakthrough. They synthesized a 3-dimensional framework that created open channels of empty space running through it. Crucially, when heated, this structure didn't collapse. It remained intact, stable, and permanently porous. This MOF was found to be able to absorb and, importantly, release gases like methane, nitrogen, and oxygen, all without changing its shape. However, Kitagawa recognized that simply making a stable, porous material wasn't enough. He needed to show how MOFs were fundamentally different from other porous materials that already existed, namely zeolites. So he published a paper describing his vision for MOFs, laying out a grand vision for what this type of material could become. He articulated their selling points. They can be created with incredible customizability, with countless combinations of metal ions and linker molecules, giving MOFs immense potential for a variety of functions. Not only that, but Kitagawa emphasized that MOFs could be soft, flexible materials, envisioning dynamic frameworks whose pores could open and close, the entire structure changing shape in the presence of certain molecules. At this point, our story turns to Omar Yaghi, a Jordanian immigrant to America whose work would transform the field of MOFs from an academic curiosity into a massive scientific endeavor. Yaghi was captivated with the idea of designing materials, but found the traditional methods of synthesis lacking. His initial research in the mid-90s led to the creation of several frameworks, one of which could be heated to 350 degrees Celsius without collapsing while its pores were occupied. In the article describing these materials, Yaghi coined the term metal organic framework. But Yaghi was just getting started. He and his team delivered the next major development in the story of MOFs. In 1999, they unveiled a material that has become famous in the field, MOF 5. This material was a game changer because it was the fully realized MOF that chemists were trying to create. It was incredibly spacious, stable, and could be heated to high temperatures even while empty. Now, the truly mind-blowing property of MOF 5 was the massive surface area it held. When Yaghi's team measured it, the number was staggering. As much as 4,400 square meters of surface area packed into a single gram of material. With just a few grams of MOF 5, a small pile of powder you could easily hold in your hand, you had more surface area than 2 American football fields combined. The innovations kept coming. Just a few years later, building on Kitagawa's vision, researchers succeeded in creating soft MOFs. These were dynamic, flexible frameworks that could literally change their shape and pore size in response to certain molecules. When filled with gases like water or methane, the material would swell and shift, only to return to its original shape when the gases were removed. These soft MOFs act almost like a molecular lung, capable of breathing gases in and out in a controlled, reversible process. This added a whole new dimension of functionality, allowing for even more sophisticated control over storing and releasing gases. With these foundational breakthroughs in place, the field of MOF chemistry exploded. In the years since, MOFs have been developed into an almost miraculous class of material, with researchers crafting tens of thousands of different frameworks, each designed with specific functions in mind. Even the iconic MOF 5 has been used as a blueprint for further innovation. Yaghi's group produced a whole family of variants based on the original structure, changing the length of the linker molecule to create a series of frameworks with different sized voids, tuning the spaces to be bigger or smaller to accept or reject specific molecules. One of these variants proved to be exceptional at storing massive volumes of methane gas, leading Yaghi to suggest that it could be utilized for natural gas-fueled vehicles. Another headline-grabbing function Yaghi's team demonstrated was the ability to harvest water from air, even in the middle of the arid Arizona desert. They designed a MOF that would absorb water vapor from the cool, more humid night air. Then, as the morning sun gently heated the material, the MOF would release its captured cargo, yielding pure, drinkable water. Although in most cases, these materials have only been demonstrated on a relatively small laboratory scale. However, the promise is great enough that investments are being made for mass production and commercialization. We are beginning to see MOFs leave the lab and enter the real world. There are companies employing MOFs to capture toxic gases produced during the manufacture of semiconductors. Other venues are developing and testing materials designed to capture carbon dioxide directly from industrial flue stacks, or even from the ambient atmosphere, aiming to reduce the greenhouse gas emissions that drive climate change. There are MOFs designed to capture crude oil from polluted water, or ones that can remove PFAS, the harmful forever chemicals associated with Teflon manufacturing, from water supplies. In a similar vein, there are MOFs that harvest valuable rare earth elements from water streams. Or there are MOFs which can store and release hydrogen gas at atmospheric pressures, making them promising for hydrogen-fueled vehicles. Name a field of study, and I would bet there's a MOF being researched in it. From environmental remediation to clean energy, from manufacturing to advanced medicine, metal organic frameworks possess such an incredible and versatile potential that they stand to affect nearly every industry and field of science. It's not an exaggeration to say that they are a class of material that will likely help define the landscape of the 21st century. The decades-long journey has given birth to a completely new way of thinking about matter. The development of this new type of material has provided chemists, and really all scientists, with a new set of problem-solving capabilities to face the numerous and complex challenges of our time. A teaspoon-sized amount of a simple powder provides a world of possibilities, proving that MOFs are capable of greatly benefiting all humankind, and are deeply worthy of winning the Nobel Prize. Thanks for watching. I was actually kind of surprised to see that MOFs won the Nobel Prize for Chemistry, not because I thought something else should have won, but because I thought they had already won the prize. But tell me what you think. What do you think is the most surprising or interesting thing about MOFs? Or maybe some of you have worked with MOFs before and want to talk about it. Let me know down in the comments. And if you want more stories about the science that shapes humanity, make sure to subscribe so you don't miss my next video.